How to determine grid dimensions for UT spot, UT scanning UT corrosion mapping, guidelines for effective ultrasonic testing grid setups. Purpose of the presentation, Introduction to Thickness Measurement Methods. This presentation introduces engineering professionals to the structured approach used to determine the appropriate grid dimensions for UT spot measurements, UT scanning, and UT corrosion mapping. The objective is to explain the decision-making logic behind why, when, where, and how each of these ultrasonic testing methods should be used across pressure equipment, piping, and static mechanical assets. It provides a comprehensive framework rooted in API 570, Piping Inspection Code, API 574, Inspection Practices for Piping System Components, API 579-1 ASME FFS 1, Fitness for Service, ASME Section 5 Article 4 and 5, Ultrasonic Examination Requirements, and API 581, Risk-Based Inspection Methodology. These standards define inspection effectiveness, corrosion morphology, and measurement requirements. Engineering professionals must understand the distinct limitations and advantages of each UT method to ensure reliability in asset integrity assessments. The content herein also discusses inspection complexities such as localized corrosion, pitting, underdeposit corrosion, and general wall thinning, linking each to its corresponding suitable UT methodology. Decisions regarding grid size, whether 10 x 10 mm, 25 x 25 mm, or 50 mm scan spacing, affect probability of detection, POD, data resolution, and long-term remaining life calculations, which are foundational to fitness for service evaluations under API 579-1. The presentation also includes comparison tables, dimension matrices, and recommended practices extracted from internationally recognized codes to support consistent and standardized engineering decisions across inspection teams. Ultrasonic thickness measurement methods differ significantly in coverage, spatial resolution, and applicability. UT spot, the simplest method, provides individual point-based thickness readings typically collected at condition monitoring locations, CMLs. As per API 570 Section 5.6, CML-based thickness monitoring is appropriate for circuits exhibiting predictable and uniform corrosion behavior. UT scanning offers improved coverage, incorporating linear or grid-based semi-continuous measurement techniques that allow detection of localized thinning. ASME Section 5 Article 4 describes scanning techniques, probe movement methods, and calibration processes essential for reliability. UT scanning is preferred for welds, transitions, supports, and any location where corrosion variability is moderate. Finally, UT corrosion mapping, referenced in API 579-1 Part 4 and ASME v Article 5, provides high-density area-based thickness data using encoded B-scan or C-scan imaging. This method is indispensable when detailed corrosion morphology must be captured for high-risk circuits or when preparing a fitness for service Level 2 or Level 3 analysis. The three modalities form an inspection hierarchy that aligns coverage, risk, and morphology to ensure suitable inspection effectiveness as defined in API 581. Why, when, and where UT spot is used, how UT spot is performed. UT spot measurements are primarily used for low-risk, predictable corrosion environments where a limited number of data points can adequately represent the condition of the component. According to API 581, circuits falling under low inspection effectiveness categories, low i.e. D or E, may be monitored with UT spot because corrosion variability is minimal. UT spot is typically applied to long runs of straight piping, non-complex geometries, and locations where stable thinning rates have been confirmed historically. API 570 specifies that CML selection should reflect representative corrosion zones, ensuring that spot UT readings are meaningful. Spot UT is widely used in systems exhibiting uniform thinning, including carbon steel piping exposed to non-aggressive environments. However, spot UT is not suitable for localized corrosion detection due to its limited coverage. API 574 explicitly warns against relying solely on point readings in environments where corrosion morphology varies. Its primary advantage is speed and low cost, making it ideal for baseline or routine monitoring under stable conditions. UT spot follows a straightforward procedure governed by ASME Section 5 Article 4. The method begins with identifying appropriate condition monitoring locations, CMLs, in accordance with API 570 Section 5.6, considering historical corrosion patterns and expected damage mechanisms. The inspection surface must be prepared by cleaning and removing coatings or scale to ensure proper coupling between the probe and the metal surface. A calibrated ultrasonic device with an appropriate frequency probe, often 5 MHz for carbon steel, is used to take point readings. Operators must measure nominal, minimum, and structural thicknesses, ensuring accuracy by performing calibration checks on reference blocks. Documentation must include thickness values, measurement uncertainties, and temperature conditions. UT spot's inherent limitation is that it offers no spatial mapping, making it unsuitable for detecting isolated thinning or pitting. Nevertheless, it remains a reliable method for trending uniform corrosion rates in accordance with API 574's best practices. Why, when, and where UT scanning is used, how UT scanning is performed. UT scanning is employed when corrosion morphology displays moderate variability and spot UT lacks sufficient coverage. Typical indications for UT scanning include visible corrosion, fluctuating historical thickness readings, and environments known for localized thinning, such as under insulation or beneath pipe supports. API 570 Section 6.2.7 identifies welded joints, transitions, and support zones as areas where UT scanning improves defect detectability. In these settings, corrosion does not occur uniformly, therefore, scanning a broader region is necessary to establish an accurate minimum thickness. API 574 outlines common localized corrosion mechanisms, such as MIC, underdeposit attack, and erosion corrosion, that require wider coverage. UT scanning enhances detection capability by allowing inspectors to sweep a probe along defined paths or grids, capturing semi-continuous data. Its intermediate coverage makes it ideal for medium-risk circuits under API 581's RBI framework. Localized thinning can be captured before it progresses to a severity requiring full corrosion mapping. UT scanning techniques are described in ASME Section 5 Article 4, which sets requirements for probe movement, calibration, scanning speed, and detection sensitivity. Scanning may be performed manually or with encoded scanners that track probe position digitally. The grid dimension typically ranges from 25 mm to 50 mm depending on component geometry, corrosion variability, and required coverage. Larger grids reduce inspection time but may miss smaller pits or isolated thinning. Smaller grids improve resolution. Prior to scanning, operators prepare the surface, confirm equipment calibration, and establish scanning lines. The probe is then moved uniformly across the grid area, and minimum thickness readings are recorded. The thickness results can be displayed as profile, B-scan, views. UT scanning provides a balance between resolution and efficiency and is often used as a screening method to determine whether more detailed corrosion mapping is required. Why, when, and where corrosion mapping is required, how corrosion mapping is performed. Corrosion mapping is the highest resolution ultrasonic inspection method, used when full spatial detail is required to characterize corrosion severity. According to API 579-1 Part 4, corrosion mapping is mandatory when conducting fitness for service Level 2 or Level 3 assessments involving localized corrosion, pitting, or complex thinning patterns. It provides detailed thickness matrices that allow engineers to compute remaining life, assess structural integrity, and evaluate stress distribution under degraded conditions. Mapping is also required when corrosion variability is high, such as in wet H2S systems, amine circuits, and high-temperature sulfidation environments. API 574 recommends area-based measurements when corrosion is non-uniform or unpredictable. Corrosion mapping is indispensable for vessels, columns, and shells where a localized defect may compromise structural stability. Its detailed output allows for precise determination of T-min, MAWP recalculations, and run, repair, replace decisions. UT corrosion mapping follows advanced procedures outlined in ASME Section 5 Article 5 and API 579-1 Part 4. The inspector defines the mapping area and chooses a high-density grid, commonly 5 x 5 mm or 10 x 10 mm, balancing resolution and scanning time. Encoded scanners collect thousands of thickness readings across the grid, generating C-scan images that show corrosion morphology in color-coded detail. Surface preparation is crucial to ensure good coupling and accurate data acquisition. Calibration blocks representative of the material type and thickness range must be used. The data collected is processed through specialized software to generate contour maps, pit maps, and minimum thickness matrices. The results support engineering analysis, including remaining life calculations and localized stress evaluations per API 579-1. Mapping offers the highest POD and is considered essential for high-risk equipment in RBI programs. Grid selection fundamentals, standard grid dimensions and application. Grid dimension selection is driven by engineering requirements, corrosion variability, and probability of detection objectives. API 579-1 provides detailed guidelines for evaluating localized thinning, stating that fine grids are required when corrosion morphology is complex. API 581 defines inspection effectiveness and links coverage levels to POD. Larger grids, 25 to 50 mm, are suitable for general thinning, while fine grids, 5 to 10 mm, are required for pitting, mic, or complex damage. Component geometry also affects grid selection. Small diameter piping may require denser data due to curvature and stress concentration. Grid size directly affects FFS calculations because minimum thickness values determine remaining life and MAWP. ASME V mandates calibration and scanning requirements that influence grid density. Engineers must therefore evaluate damage mechanisms, risk, and structural significance when selecting grid dimensions. Standard grid dimensions vary by inspection method. UT spot has no grid, as it relies on discrete point measurements at CML locations defined in API 570. UT scanning commonly uses 25 mm or 50 mm grid spacing, aligning with ASME Section 5 Article 4 recommendations for typical probe sizes and the need for semi-continuous data. Corrosion mapping grids range from 5 x 5 mm to 25 x 25 mm. API 579-1 references fine grid requirements for pitting assessments under Part 4, recommending a resolution appropriate for identifying critical pit dimensions. ASME Section 5 Article 5 requires encoded data acquisition for mapping, enabling high-density grids. These grid dimensions ensure coverage appropriate to the severity and morphology of corrosion, supporting safe engineering decisions regarding run, repair, replace strategies. Comparison of UT spot, scanning, and mapping. The three UT methods differ significantly in coverage, resolution, risk applicability, and cost. UT spot offers minimal coverage and is used for low-risk circuits with uniform corrosion, per API 570. UT scanning offers medium coverage and improved detection for localized thinning, useful for medium-risk circuits under API 581. Corrosion mapping offers full coverage and the highest POD, supporting fitness for service decisions under API 579-1. Scanning grids, 25 to 50 mm, are more efficient but less detailed than mapping grids, 5 to 10 mm. Spot UT has limited defect detection capability and should never be used for pitting environments, as stated in API 574. Mapping provides full corrosion morphology and supports engineering calculations that cannot be reliably performed with spot or scanning. These differences allow engineers to match inspection techniques with damage mechanisms and risk levels appropriately. Decision logic and summary. Selecting the appropriate UT method requires alignment with damage mechanisms, API 571, risk ranking, API 581, and inspection intervals, API 570. Spot UT is suitable for predictable, low variability corrosion. UT scanning is appropriate for environments with moderate variability or known localized thinning risks. Corrosion mapping is required when corrosion is complex or when detailed fitness for service analysis is necessary under API 579-1. Grid sizes should be chosen based on the desired probability of detection, component criticality, and expected corrosion morphology. Choosing the wrong grid size or method can produce misleading data, resulting in incorrect remaining life calculations or unsafe run, repair, replace decisions. Therefore, standardized selection based on internationally recognized codes is essential for asset integrity and safe operation.